Welcome, AP students. Happy Monday to you. We are going to continue on our Unit 6 Thermodynamics section, and we're going to pick up with some example problems. So I have several example problems in this particular section as we continue on our journey of reviewing enthalpy and calculating enthalpy in the 4 ways that we're going to learn to calculate. But I have a couple example problems here, beginning with doing work and calculating energy from work and change in heat. So the first problem I have here is if the internal energy is increased by 378 joules, while 75 joules of expansion work is done, how much heat was transferred and in which direction? So let's look at this right here. So right here we have energy. So we have our change in energy equals Q plus work, which is W in this case here. So let's look at what we're given here. So it says the energy was increased by 378. So that's our change in energy. So increase, which is going to be a positive number. So we have 378 joules equals. It says while 75 joules of expansion work was done. So we're trying to calculate heat transfer, which is Q. So let's think about this. So expansion, so for it to expand, it's going to be negative joules. If it was contracting, it would be positive. So that's the one that's kind of sometimes counterintuitive in to think on that. So this here means we have minus, and this is going to be 75 joules because it's expanding. So our change in heat, so basically we would go ahead and add 75 joules to each side plus 75 joules. So in this case here, Q is going to equal to, let's plug this in here, 378 plus 75. So we have 453. So 453, and that is positive. So the heat is going to transfer into the system from the surroundings. So the surroundings are going to contribute that many joules. And right there, that would be your answer on this particular question. Hopefully, try and pause the videos and try and work out some of these problems. These are nice examples to refresh your memory on some of these components that we've been looking at. Let's look at the next problem here. It says, piston expands against 2.5 atmospheres of pressure from 11.5 liters to 29.1 liters as 1,035 joules of heat is absorbed. So calculate the change in energy. So we have here our delta E equals Q plus W. So we have here some heat exchange right here. Heat is absorbed. So we have delta E is going to equal 1,035 joules. So we're going to have to calculate work. So if you remember, work equals the pressure times the change in volume. That is a formula that we learned previously in the last lesson. We talked about this. All right. So it says the pressure. So let's use it right here. We got it given to us. So we have pressure is 2.5 atmospheres. And our volume is volume final, which is 29.1 liters minus 11.5 liters. So we're going to have here 29.1 minus 11.5. So we're going to have 17.6. So 17.6 liters. And we're going to multiply that by 2.5 atmospheres. So we're going to have 2.5 times 17.6 15.6. So we're going to have 44.0. Actually, we have 2 sig figs here because we're multiplying. So we'll just round that at 44, and that's atmospheres times liters. So remember, there was a conversion that we had saw last virtual lesson, 101.3, and that is joules divided by atmospheres times liters. So that's a conversion factor that we're going to be looking at. And I did not place this negative in here. That I failed to drop that in there. So this is a negative. Work is being done, so it is a negative in this case here. It would have been a work is being done on it if it was not expanding, it was contracting. So that this was expansion, which means it's being done. So please keep that in mind. This was the formula right here. I just failed to place that negative in the front of it. So here is, we got to do a conversion here. So we have negative 44 atmospheres times liters over 1 times, and we're going to put 101.3 joules, and this is atmospheres times liters. So now we'll just cross these guys off, and then we will multiply this out. So we have 44 times 101.3. So we have a big number here. So we have negative 4. Then we have, let's see here, 2 significant figures. So 4457.2. So to round to 2 significant figures, we're going to go 4,500 joules. So now we can come back here and plug this in, and this is a negative number. So we're going to come up here and plug this in. So plus 4,500 joules, and this is negative. So now let's calculate our change in energy. So we have 1,035 minus 4,500. So we're going to have a change in energy of negative 3,465 joules. So that's our change in energy. So it released a lot of energy, this particular work, this example here, this problem here was negative enthalpy change in energy. All right, so 4 ways, just a quick review on this, 4 ways to calculate change in enthalpy. We have calorimetry, which we've done several problems on calorimetry previously. We're going to look at, again here, average bond enthalpy. So key notes to remember here is reactants minus the products. And for this particular one, you have to draw your Lewis structures, because bond enthalpy is you have to look at how many bonds you're breaking. So real important. Next, you have enthalpy of formation. And that is 0. That's key note is, remember, 0 for an element in its natural form. So a diatomic molecule, things like that. So that's your enthalpy. And then you have Hess's Law, which we'll practice that as well. So let's get started on these. Calorimetry. So we have 100 grams of iron at 98 degrees Celsius is placed into 200 grams of water at 25 degrees Celsius. What will be the final temperature? So we have to set Q to Q. So Q equals MCAT, so we're going to set it up. So we're going to come over here and we're going to go negative Q of, and we're going to say this is the iron, Fe, equals the Q, and we're going to say this is H2O. So you got to calculate, get C, the C value. So let's just set this thing up here. So we have negative MC delta T equals MC delta T. So let's look up our C because they're different. And these are on a standard chart. You don't have to have these things memorized. So let's begin filling in our information. We'll look on the chart and get our specific heats for iron and water. So the mass of the iron is 100 grams. So we're going to go in negative, and this is 100.00 grams. Our C, let's look up here what C is. It is 0.45, so we have 0.45 joules per gram Celsius. And then we have here placed into at 25, this was at 98 degrees. So we have our temperature. Temperature initial in this case here is 98 degrees. And now here we could cancel off grams, and then we'll get our Celsius going here in a second. And we have our joules that we will be taking care of. So now let's look at the other side here. So let's set that equal. So we have this. So we have 200 grams. So 200 grams. To 100.00 grams. Our water chart, water is 4.184, so 4.184, and that's joules, and that is grams degrees Celsius. And then here we have, it was 25 degrees, so temperature final minus 25 degrees Celsius. All right, so now we're going to do a little math on here. So let's get started. So we have 100 times 0.45. So we have negative 45. And then we have TF minus 98 equals, and on this side here we have 200 times 4.184. So we have 836.8. And now we have temperature final minus 55 degrees Celsius. So now we'll go ahead and do some foiling on this here. So right away I have negative 45 temperature final. A negative and a negative is a positive, so I have plus, so I have 45 times 98, so I have 4,410 equals. So now I have 836.8 temperature final minus, so I have 836.8 times 25. So I have 20,920. All right, so now I want to get rid of my negatives. So I'm gonna go ahead and add 45 plus 45 temperature final, and I'm going to add 2920 to each side, plus 2920. So now I'm going to have here 836.8 and I'm going to add 45. So I have 881.8 temperature final equals. So now I have 2920 plus 4410. So I have 25330. Now I'm going to divide both sides. So I'm going to go 25330 divided by 881.8. So my temperature final is going to equal, and I should be at two significant figures. So I should be at 29 degrees Celsius. So that is a calorimetry problem. Hopefully you remember doing some of this type of work, and it comes back to how to do that. 29 degrees Celsius for 2 sig figs. All right, next we're going to look at average bond enthalpy. So this is where the Lewis structure comes into play, because you have to break each particular bond. And when you talk about bond enthalpy, it's the sum of the total of the reactants minus the sum of the total of the products. So let's take a look at an example. So you'll always have to be given a chart. So instead of looking up here, there's a chart for us right here. So we're going to look at that in our solving of this. It says hydrogen gas reacts with chlorine gas to form gaseous hydrochloric acid or hydrogen chloride. So let's look. It says calculate delta H. So let's write our formula, because we're going to need that. So I'm going to come over here. I'm going to go H2 plus Cl2 reacts to form 2HCl. So I am all balanced. And this is, when we talk about this, is the change in sum of the reactants minus the sum of the products. So now I have to look at how many bonds of each are going to be broken out here. Okay, so I have HH bond, I have one of them here. So this is going to be 432, and this is kilojoules per mole. And then I'm going to, and this is the reactants minus the product. So I have plus I have 239 kilojoules per mole here. And I have to add these guys together. And then minus, I have two of these, 2 times, in this case here, I have 427 kilojoules. So now let's get this calculator and put this together. So 432 plus 239. So I have on this side here 671 kilojoules per mole. And I'm going to be minusing 2 times 427. So I have on this side here 854 kilojoules per mole. So my delta H is going to equal 671 minus 854. So my change in H is going to be negative 183 kilojoules per mole. And that is my change in energy in this based on bond dissociation energy. All right, so that's one example. I have another one right here we're going to look at. So here's a little bit more of an in-depth one. So we're going to have to do a little bit of calculations here. So calculate the bond, the change in enthalpy for the combustion of methane. So I have my methane, so I'm going to write my formula here. So I have CH4 plus O2 reacts to form CO2 plus H2O. So when I look at this here, I have to balance my hydrogens, and that gives me 4 oxygens. So I come over here and balance it. So now that's important, because now I have understanding of how and what's happening. So you have to draw the Lewis structure because you have to see each bond, but I'm pretty familiar with these particular Lewis structures. So we have C, H, 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 H. I have my O2 is going to be something like that. My CO2, if you remember the carbon's in the middle, and I double bonded on each side to oxygen. And then we know our classic H2O. Like that. So now that gives me an idea of what I'm going to be doing here. So I'm going to take the sum of the reactants. So I have the sum of, I have 4 bonds, and each one of them is 413 kilojoules per mole. Plus I have 2 of these, so I'm going to have to put 2 times, and that is 495 kilojoules. I'll put this all here in a bracket. Minus my product, and my product here I have, when I look at this right here, I have 2 bonds right here that have to be broken. So I have 2 times 745 kilojoules, plus I have 2 H2O. So I have a total of, you see, 1, 2, 3, 4. So I have 4 times 467 kilojoules. And I'll put this all in brackets. So a lot going on this. So now I can come 4 times 413. So I have 1,652 kilojoules. Plus, now I have 2 times 495. So I have 990. Kilojoules minus, so 745 times 2, I have 1,490 kilojoules, plus I have 4 times 467, and this is 1868 kilojoules. So now let's work on finishing this up. So 1652 plus 990 is 2,642 minus, and on this side I have 1,490 plus 1868. So I have 3,358. So my change in energy, or my delta H, is 2642 minus 3,358. So is a negative 716 with this particular problem. So I have this combustion reaction. It's releasing 716 kilojoules per mole in this case here. So that is using bond enthalpy. So now standard heat of formation. So this is slightly different. We have sub naught, delta H sub naught with that little zero sign, that little symbol on the top there. And this is enthalpy of formation. And in this case here, I find my formation enthalpies and I go my products minus my reactant. This is given to you. This one you do not have to know. If you look at your delta H sub naught, it's your standard enthalpy, and it is delta H sub naught of formation of products minus reactants. So that is how, in fact, we will solve this. So let's get started on this. So enthalpy of formation. So ammonia reacts, so let's just write our formula down. Ammonia reacts with oxygen, so I have NH2 H3 plus O2 form nitrogen dioxide, reacts to form nitrogen dioxide plus water. It says calculate the delta H using the enthalpy of formations. I have my little chart right up here provided to me. I got to balance this equation here. So I see 2s and 3s on my hydrogen. So if I put a 2 in front here, that would give me 6 hydrogens. So if I come over here and put a 3, I have 3, and that would be 7. That's an odd number, so I can't use that because my oxygens won't balance. So if I put a 4 here, let's work this one out here, then therefore I'd have to put a 4 in front here. So I have 4 nitrogen, 4 nitrogen. I have 12 hydrogens, so I need to put a 6 here. So it's 12 hydrogens. So now I have a total of 6 and 8. So 14. So I got to come over here and put a 7. So now I am balanced out. Okay, so now it is, remember, it is the sum of the products minus the sum of the reactants. So, and our coefficients come into play as well on this. So let's get our product. So here I have 4 times NO is 34 kilojoules, 34 kilojoules, and then I have plus 6 times water, which is negative 286 kilojoules, bracket this, and then minus my reactants. So I have 4 times, as a bracket, 4 times my ammonia, which is negative 46 kilojoules, plus I have 7 times natural state, 0. Close my bracket. So now let me get my calculator again here. So I have 34 times 4. So I have 136. So 136 kilojoules. Plus, I have 6 times 286, and that's negative. So I have a negative 1716. So let me just finish this one out right here. So 136. So I have here 1716. So I have a negative 1580, and it's going to be minus. So let's go ahead and take care of this side now. So I have 4 times 46. So I have a negative 184 plus 7 times 0 is 7 times 0 is 0. So now let's calculate this. So I have 1580 negative plus, because negative and negative plus 184. So the delta H sub naught is going to equal negative 1396 kilojoules per mole. And there is my final answer on that. So slightly different, but hopefully you remember how to perform these. So last one is Hess's Law. So Hess's Law states that for a chemical equation that can be written as the sum of 2 or more steps, the enthalpy change for the overall reaction is the sum of the enthalpy change for the individual steps. So we have these elementary steps, and then we're just going to put it together. So let's take a look at our final example here. So here we have our overall, and that's what it's asking for. It wants us to calculate the overall delta H of this particular reaction. So let's look at what we got going on here. So when we look at the first reaction, I'm going to label these as 1, 2, and 3. We look at the first one. I have my ammonia on the right side, but I have 4 of them. So I have to double it. So I'm going to multiply this by 2, and I've got to multiply this by 2. So if I do that, I'm going to write it over here. I'm going to go 4NH3. I'm going to have 2N2 plus 6H2. And then I have 92 times 2. So I have 184. So I have 184 kilojoules. Now let's look at the next one here. Well, I have to have the water on the other side. I have it on the wrong side here. So I need to reverse it, and I need to triple it. So I've got to reverse N triple, which means I got to reverse and multiply by 3 here as well. So now I'm going to do that. So I'm going to reverse it and multiply by 3. So I'm going to have 6H2, so 6H2 plus 3O2, my arrow, and now I have 6H2O. And I'm going to reverse the sign and multiply by 3. So I have 572 times 3. So now I'm going to have here negative 1716 kilojoules. Now my final step here. All right. It has to stay in this order because I got to cancel off the N2 on number 1. But I have to have 4NO, which means I'm going to have to double this one. I just have to double it. So if I double that, I have to double this as well. So I'm going to come over here. I'm going to go 2N2 plus 2O2 reacts to form 4NO. And I have to multiply that by 2. So I have 180 times 2. So I have negative 360. So let's see if this all works out as it should. So when I look at here, I have my N2s cancel. My H2 cancels. So it comes out to 4NH3 plus 5O2. I have 4NO plus 6H2O. And that is exactly, these are the same. So that worked out great. So now, according to Hess's law, all I have to do is add those up. And that will be my change in enthalpy. So I have 184 minus 1716 minus 360. So my delta H equals negative 1892, and this is kilojoules per mole. And this is using Hess's law. So we have done examples of each and every one of these problems now, giving us a little bit of idea on how to solve for the enthalpy change in a reaction based on calorimetry, based on average bond enthalpy, enthalpy of formation, and Hess's law. So thank you for watching. Please don't forget to go on and do your AP Classroom. There's 2 quizzes for Unit 6 review. It is a short multiple choice and 2 free response. So please don't forget to do those. And we'll have our test upcoming here on Thursday. So thank you for watching. Go in peace.